Okay, hello. My talk is going to be about complex K-theory and complex periodicity. So let's start with what the K-theory actually is, and we will, in this talk, I will use two notions of K-theory, mainly just regular K-theory and reduced K-theory. So suppose we have Hausdorff compact space. So it is sufficiently nice for us, and we will consider the space of all vector bundles, all complex vector bundles. Yes, the set of it's just a set. This is a space. Yes, the set of all C vector bundles. And let's consider some equivalences on this set. First equivalence is just so let's first see the some elements of it. For example, we have a trivial bundle of dimension n. And we will denote it by epsilon to the power n. And let's consider let's consider some equivalences on this set. Firstly, the stable equivalence. Two vector bundles are equivalent. Let's see what is the good. Yes, E. Two vector bundles are equivalent if there exists some n such that E1 plus epsilon to the power n is isomorphic to E2 plus epsilon to the power n. So if we consider large enough trivial bundle, if we this set obviously has now I am sure that for this equivalence that this is the same n. So the next equivalence is that there exists n and m such that E1 plus epsilon n is isomorphic to E2 plus epsilon m. So these are two different equivalences on this set. So the first equivalence, so suppose we factor this set by this equivalence. Let's see. By this equivalence, then we get reduced K-theory of X. We just get the reduced K-theory, and no more words need to be said here. But if we consider factor by this equivalence, we will not. Firstly, we can see that this is actually a group because there is an operation being the the sum, and it is actually invertible because for for every sufficiently large for a sufficiently large n, we can embed E to the sufficiently large trivial bundle, and after this we can get the not tangent but the perpendicular bundle to this, and in this group E perpendicular bundle plus the original bundle gives us epsilon n, so it is actually equivalent to 0. So 0 is epsilon 0, operation is the plus, is the sum, and there is also there are also the inverses. So it is actually a group. We don't need anything. We don't need anything to say that this is a group. But if we consider the factor by this equivalence, it is not yet a group, because suppose we have an inverse to epsilon 0. Yes, to the neutral element. Yes. Yes. So if we consider this definition, the dimension of the bundle must be equal to 0. So the only invertible element is the epsilon 0. But we can consider the operation, as we know from, for example, getting all the okay, for example, getting all the I'm forgetting the words. Целые числа по-английски как будет? Yes, the integers from the natural numbers. We can consider the formal differences of two bundles. So k of x is the set of formal differences E1 minus E2, E1, E2 live in vector C, and yes, and this we can consider factor the stable equivalence. So, for example, we get the bundles with the negative dimension, just considering epsilon 0 minus epsilon n, for example.
Okay. By the way, the construction which takes a semi-group and produces a group is factorial. It's also a joint to the forgetful functor from groups to semi-groups. So we have two functors. We have a forgetful functor and another functor. Which one is the left joint and which one is the right?
Forgetful functors are I always forget it. It is maybe they are right, but let's try to remember this.
Let's try to figure it out.
So let's first consider it as a right functor. So what's the name of the functor from groups, from semigroups to groups? What's the name?
Well, I don't know. Let's say the Grothendieck construction.
Okay, Grothendieck. So we have okay. Let's do it from the next board. So there are semigroups and groups. This F and G, G forgetful, and F is Grothendieck. Let's like this, and suppose F is left adjoint, G is right adjoint, then left functor semigroup, the name of A, B, this is in group semigroup in A, G of B. Am I right? So if we consider this as a forgetful functor, so it is
If we have a map of semigroups from A to B, where B is a group, but we consider it as a semigroup. Well, we automatically have a map of groups from the Grothendieck construction to B, just by
yes.
taking the f of x minus f of y. Okay, where x and y is the coupling which participates in the Grothendieck construction. So yes, this is correct. Does everyone agree? Okay, so we well, this is the usual situation. We have one functor which is the right adjoint. So the other one is a left adjoint.
Yes. So I had a disaster of a name, being G forgetful functor and F Grothendieck, but okay. So okay, it is right adjoint forgetful, right adjoint Grothendieck group functors.
These numbers here in this definition, we take that up to bundle isomorphism as a semigroup. So why do we need the first definition at all?
Wait, what do you mean?
Well, we get the K-theory if we apply the Grothendieck construction to the semigroup
Yes.
of the isomorphism classes of vector functions with the additional operation. It's a semigroup, it's not a group, it's a semigroup, so the Grothendieck construction is applicable.
Well,
Why,
yeah,
what do we need the first version for?
well, wait, no. Something's not right, yes? Because we need to distinguish between we need to distinguish between epsilon 0, epsilon 1, and so on. If we consider only this, we do not distinguish between them. Так. Первое распределение вот это, в смысле? Или вот это? Сейчас. Сейчас, да. Ну да, это, конечно, правда. Да вроде нет. Ну, как бы... Ну, сейчас. Ну, оно, конечно, полезное, наверное, в принципе. Не, ну да, ну да, это скорее замечание, чем нужное определение для определения. Because in the semigroup all the stable equivalent vector bundles will be equivalent to one another, because we can get epsilon minus one minus epsilon n.
Which bundles will be
E1 and E2. So
if E1 and E2 have the same rank and the stable equivalent, then they're equivalent to
yes, so they will be equivalent in K of x. Yeah, so this is more of a just maybe intuition, maybe some note about what is happening in K of x. Okay. So we have a group structure. We also have a ring structure, because we have on vect C of x we have tensor product. Vect C of x. Vect C of x. Moreover, if we consider on regular K of x, tensor product is compatible with the Grothendieck deconstruction. So tensor product is actually gives us ring structure on K of x, and epsilon 1 being a unit. Yes. Yes, I forgot to say that that if we maybe this is where, not really. So we have a map from K of x to from K of K reduced of x, reduced K theory of x to K of x. Just it is tautological. Wait. No, we have a map. We have maps in both directions actually, but let's see. Suppose we have suppose x has a base point, then we have a map from where to where? We have a map from yes, we have a map from here to here if we have a base point. If x is x0, okay, if x is a base space, a space with a base point. Base point x0. We have this map sending so what I'm trying to say is that as a usual reduced homology, k of x is reduced k theory of x plus z. This is what I'm trying to say. So why is that? Because we have all the trivial bundles epsilon n are zeros in here. Are zeros in here because they are stably equivalent to epsilon 0. And they are so if we consider a map from that's the tricky part, from here to here, from k of x to reduced k theory, the kernel of this map is just epsilon are just epsilon n's, are just trivial bundles. So that's why we get the splitting. We do not get the splitting yet. It is just map in one direction, and the splitting occurs when we have the map in the opposite direction from k prime from the reduced k theory to regular k theory when we have a base point, because if we have a base point
So suppose we have a stable equivalence class of vector bundles. You map it to itself, comma 0, which is a well-defined element of k of x.
yes, but it is actually as I remember, it is important that x has a base point, because if we have
Okay, so for any cohomology theory, the reduced version is the co-kernel of the map from some vanilla one-point space to the cohomology of our Hilbert space. Every space X maps into the one-point space ET, which is not necessarily the base point, just some one point space. So we have the co-kernel, and the co-kernel is the K2. And in general, in the non-base case, this is all we have. So K tilde is quotient of K. And now
Yes, yes,
this,
yes.
we need another interpretation as the cohomology must point to which point? Well, here's where we need the base point.
Yes, yes. I was not right because we need. If we have x0 in x, then we have. Wait, no. Yes, this is true, and because k of x0 is just z. We have this because we have x0 in x, because we have a pullback. Yes. So okay, we have the splitting, and as it is a ring, and we have this map from k of x to k of x0, we might consider the kernel of this map, which is isomorphic to reduced K theory. Yes, kernel of I star is isomorphic to reduced K theory, and as it is a kernel, it is an ideal, so it has also a ring structure, but maybe it does not have a unit. Yes. Okay. So we have just an internal multiplication, and we also have I don't remember, something like external multiplication. So suppose we have we want to have the map from k of x tensor k of y to k of x times y. I want to have this map. Let us name it mu. And how can we do that? We have two projections from the product to x and to y. Suppose we name them P1 and P2. So we can have, suppose A is in k of x and B is in k of y. It goes to P1 to the pullback of A times pullback of B. So this is a map, and it is also a ring map, because if we consider a multiplication, this is a ring. These are two rings. Suppose we have a multiplication like this: x, y, x times y. Let's consider the multiplication here being this star sign, z times t. Consider it as xz times yt. We can see that this is indeed, this mu is a ring map, because suppose we have A times B, this product is tensor D goes to P1 star of A, tensor P2, just P2 star of B, P1 star of C, P2 star of D. It goes to, it is just P1 star of A, P1 star of C, P2 star of B, P2 star of D, and this is just P1 star of AB, tensor P2 star of D. This is mu of. So it is a map of. It is a ring map. So we have this external product, and the case which is interesting to us is when y is equal to two-dimensional sphere. So there is a map from k of x tensor k of S2 to k of x times S2. So this is the interesting case. What we actually what do we actually want? We want to see. So let's consider the fundamental product theorem. Let's go to the first board. So what do we know about K-theory of S2? So we have, apart from the trivial bundles on S2, we have also a canonical line bundle on S2, because S2 is homeomorphic to CP1. Tautological. So I also.
These are not the same. By the way, how is the canonical bundle connected? In the case of P1, what's the difference between the canonical bundle and the tautological? What's the canonical bundle of P1? Okay. What's the term class of the canonical bundle of P1? Okay. What's the Euler characteristic of P1? Anyone?
It's 2.
Right, very well. So this is the Euler class of the tangent bundle. The canonical bundle is the cotangent bundle, so the Euler class will be -2, and the Chern class will be -2 as well. And the tautological bundle has the first term class equal to -1. So the canonical bundle is the second, is the square of the tautological.
Okay. Okay, so I am a bit confused, but let's continue. Okay, suppose we have tautological bundle on CP1. So we have tau and the fact wait, tautological has wait, we need canonical, I suppose, because what we want to show that we have a canonical line bundle on CP1, and we need to show that h times h plus 1 is equal to h h plus h times 1 plus 1 is equal to, wait, no, I was right, h plus h. So suppose we have so what do we need to see? We have CP1 S2 is two disks, two hemispheres, D2 plus.
Okay, so in which group does this take place?
In K of X. K not reduced, because we have 1. Why do we need this? Because this is equivalent in K theory that h minus 1 squared is equal to 0. So we have two hemispheres which are intersecting by a sphere by an equator. Is equal to S1. So suppose so we know that a bundle is trivial over the contractible space. So the only interesting part is the only interesting twist may occur only on the intersection, which is S1. So we will consider S1 living in C as a set of complex numbers of module 1. So it has a coordinate z. And let's consider the gluing function between, it is actually called Clatchin function, between two these disks being just multiplying by z. So over this it is there is a trivialization over d plus, there is a trivialization over d minus, and the thing that glues them together is multiplication by z, which is a coordinate in S1. So this is a canonical line bundle, as it said. And why is this true? Because we have what is this bundle? This is the bundle which is what is the Clatchin functions? What are the Clatchin functions of this bundle? These are both two-dimensional bundles. This is the first Clatchin functions, and this is the second one. And they are homotopy equivalent because we can just how to say it? Just take this z and take this multiplication by z and by rotating this.
Does anyone understand what's happening?
So okay, S2 can be represented as two disks glued by S1 by their boundary. We can consider this S1 being embedded into C as a set of module 1 vectors. And over both hemispheres, there is a trivialization, and the only interesting part occurs when on this S1. So yes, the two matrices. We have two-dimensional bundles. So the two matrices are these gluing functions on. So over every S1 there is an element of linear group which connects the two trivializations. Over one disk and over another. No.
So the one, the matrix on the left is the one we use for the bundle on the left, and the matrix on the right is the one that we use to do the bundle on the right.
Yes, and these are actually homotopically. There is homotopy between two of these. Homotopy as homotopy of maps from S1 to GL2 of C. Yes. Why? And why? Because we have a map. So the intuition behind this is. Okay, so as I remember it, we have a map of T which switches to two components of C2, just rotating them. Rotation of yes, and the something like the angle. So rotate. So we need the homotopy. So it is. So it is rotating it. So it's rotating it with the parameter t. Wait. Maybe that's not right. Well, maybe that's not true, but maybe this is not true, but what I'm going to say will be true for some definition of alpha t. So this one, this is suppose f1, this one is f2. Wait.
Well, the easiest thing to do would be to first consider loops in GL2, and then we can use the determinant map from GL2 to C star, which takes the matrix and takes the determinant. Well, this map produces an isomorphism of the binomials. Now, what happens with but here we
это разве... Свободные петли, это которые могут начинаться где угодно. Или как?
Значит, свободные петли — это отображение гипотетических классов, отображение из S1. Не обязательно преобладающий базовую точку и базовую точка еще может быть.
Вот, значит, ну,
Значит, апиатим — это гомотопические классы петель по гомотопии, которые сохраняют единичную точку. Вот спрашивается, как свободные петли связаны просто. У меня есть P1, значит, как мне посчитать классы свободных петель? Как мне их описать в терминах P1?
ну это сейчас. Ну там же вроде важно только это, то, в какую компоненту связанности мы попали. Ну, компоненту линейной связанности. Нет?
Вот, замечательно, да, именно так. Значит, P1, в смысле свободные петли, это класс сопряженности. Но если группа Абелева, то в ней все сопряжения здесь сопряжены. Поэтому класс сопряженности — это то же самое, что линейный. Значит, того, детерминант, да, и в данном случае, мы там вместо петель можем рассматривать свободные петли, получим то же самое. Значит, того, применим отображение детерминант, получим, что z в квадрате равно z в квадрате. Значит, после композиции с детерминантом мы получаем одно и то же в буквальном смысле отображение из S1 в C со звездой.
Окей.
Значит, поэтому как как петли, а значит как свободные петли, вот эти две штуки гомотопные.
Окей. Окей, I see.
Гомотопные как петли, но мы по секрету знаем, что ну, собственно, их нет. Если они гомотопные как петли, то что это гомотопные как свободные петли. Ладно, в общем, значит, здесь применить детерминант.
Okay. So we have this this equality in K of S2. So we have a map from H times over 2 to K over 2. We have this map. So we have a map from this. We can tensor it with K of X and get a map and compose it with the external product. So H times H minus 1 squared tensor product K of X to K of S2 tensor K of X to K of X times S2. So we have this map and theorem called fundamental product theorem. Says that the composition is an isomorphism. So
Well, let's just note that z of h by h minus 1 squared is not too big. It has as an abelian group, it has rank equal to 1. 1 squared is just generated by 1 and h, so there's nothing else, and then how do we multiply h plus h? Well, we just use the formula. And what does the formula tell us? H times h is equal to what?
To h minus 1.
H plus h, sorry, h times h is equal to 2h minus 1.
Yes.
Okay, and this well, it's not a large ring, but it's a ring. Anyway, so let's see why this is actually the KLS2. So we have constructed. We have.
So yes, I'm not going to prove this because it is too technical, but I have a corollary of this. Suppose x is equal to a point, then k of a point is just z. So we have an isomorphisms of these two rings. Yes. Okay, so this is the main. So this is the starting point, and from this we can prove the Bott periodicity. So let's start. Let's start noticing something. So.
Про эту теорему мы сейчас забываем, но мы сразу причетные вещи.
Да, это правда.
Так, ну хорошо, значит, это еще одна потенциальная тема для доклада, просто группа анализ. Хорошо, а что тогда такое периодичный сбор? Тут мы как раз сейчас узнаем, да?
Да, ну до нее еще там сколько-то времени нужно. Вот. So let's start noticing some exact sequences. So the exact sequence which is not really surprising for this course. Suppose we have the pair xa, then we have a cofibrillation sequence. So wait. Let's not. We have from here to here to here, so it is here to here. We have a in x, x factor a, which is the same as this. Then we have not sigma, but the suspension, the usual suspension of A. This is Cx, if I remember it correctly, and so on. Sx. So we know this cofibrillation sequence, and we also have the similar one in K-theory, but in the opposite direction, of course. so on. And why is this exact? Because suppose we have in here, for example, why do we have suppose so it is is it
At this point, we probably need to say something about elements, about the elements of K tilde being classified by maps into the
why do we need this? So so how do we do this? So that this is the composition of two is 0 because it is obvious. Yes, and why is it exact? Suppose we have so
Suppose we have a bundle of X, which is
yes, so H is
stably equivalent to 0. No, well, suppose
H.
we have a bundle over X, which is stably equivalent to 0 over A.
yeah, so H is trivial over A.
Not necessarily trivial. Stably equivalent to
Okay.
0 over A.
Okay, maybe. So yes, I'm not sure about being reduced. Yes. So yes. So H is okay. H is stably trivial. So suppose H prime is stably trivial. Let's consider let's consider just trivial map, adding some number of epsilon m. It's trivial. So it will not give. It will not have. It does not have problems because after going to KFA, it will be 0 as well. So we can suppose that H is trivial over A. And yes. So then there is some trickery to say that H is actually trivial over some open neighborhood of A.
Well, let's assume that we have the same quality, not H itself, but H plus epsilon. H prime plus epsilon m equal m.
It is H. So we don't need we don't want to work with stably trivial. We want to just work with trivial over A, and we can do this because it will not give us problems after we the map will forget the epsilon m. So the result is the same, and this one is also the same. We want to be just trivial over A, and some trickery to say that it is actually over some open neighborhood of A. It is trivial over some neighborhood of A, and after this we can glue the A together by and suppose E is a total space. E to X is a total space of H. Then we can consider an equivalence relation on P minus 1 of A, being being x v is equivalent to so yes, as it is trivial over A, we can consider a trivialization. So in this trivialization, xv is equivalent to yv, and after we consider the gluing by this equivalence relation, it will be the bundle over x factor A, and it is so with the trickery to be trivial over some open neighborhood of A is to give a trivialization near the point A. So we just have a trivial bundle and we glue it like a trivial bundle. Yes, so we have this exact sequence, and suppose that X is the union of A and B. Well, just not just a union, but a wedge sum of A and B, and the base point is their intersection. Okay, we can so we can consider this this sequence, and we get that K of A, K of X, K of B, K of SA, and so on. And so there is a splitting, and because there is a map to here, so because there is a map to here, which is induced, for example, which is induced by gluing A, collapsing A, yes. Yes, so we get that we get the splitting that reduced K theory of X is reduced K theory of A plus reduced K theory of B. And if we consider a special case of this, so suppose we have we know that a smash product of X and Y is X times Y factor X wedge Y. We know this, so we consider this. We will consider wait. Yes, yes, everything's okay. We put this. Yes. So next we know that a smash product is this factor. product by which sum. So let's consider this sequence for this space and this subspace. So it is smash y, which we know is which we know splits. It goes to this goes to this goes to let's say that it is this one is not obvious, but it is true to homotopy, up to homotopy, because
Because the wedge product distributes certain sums.
yes, over
Almost the case. Sorry,
the
smash product distributes over wedge sums.
yes.
Anyway, so this one splits as well.
So yes, so this one splits as well. So we have
Basically, for the same reason, we have a map from k of a plus k of b, which goes back into k of x cross y.
so yes, so we have a splitting of reduced K theories of a product is reduced K theory of a smash product plus plus K theories of the of x and y. Okay, so this is what we need, and I forgot. So we have. I think I needed the thing I erased. So we need to remember what was the external product. We have a map. Okay, let's try to write it here. So we have a map from k of x tensor k of y to k of x times y, namely being a tensor b goes to p1 p2 star of b, p1 and p2 being the projections. So we now know something about reduced K theory of the product. So what we know, A is an element of reduced K theory of x. So it must be 0 in the component k of y, because it is just it is 0 on it. It is because it is 0 on it. And this one is 0 on k of x, k reduced K theory of x. So the product is 0 on these two components. So it is so it all goes to this component. So actually
Let's identify k tilde of x inside k tilde of x cross y. What is it?
K tilde of x is so we remember from here that
Well, this is the image of the map of the k tildes induced by the projection to x.
yes. Yes.
And so the claim is if we take two elements of k tilde, the product will necessarily be in the k tilde of x wedge y. Well, y. Sorry, x smash y. Well, if this were the case, then we could project it back to k tilde of x by just taking the embedding of x into x cross y, and then we get 0 y.
Mm.
Well, because if we take an element of, so we have the following thing. We have an element of k tilde of y. And then we take the projection to from x cross y to y, pull back, and then restrict to x. What we get the map from x to y. So the map of the k tildes can be factorized as a map which goes through k tilde of a point, and we know that the k tilde of a point is 0. So the result is 0. Does this make sense?
So yes. So this map actually factorizes to this.
This gives us a product which takes two elements, one k tilde of x, the other k tilde of y, and the product is inside k tilde x smash y.
Yes. So if we consider, so now let's consider the map. Let's consider y equal to S2. We know that smashing with S2 is with S2 is double suspension. So k tilde of double suspension. So we know there exists this map. So suppose we have so yes, we know that we know this. So yes, so
if we take h inside k tilde of S2, then restrict everything to this. Basically, we want to show that time zero with h is a nice.
yes, we know that k tilde of S2 is just that h minus 1. So this gives us actually an isomorphism between k of x and double suspension of x.
What does this mean? Zero h minus 1.
It is so h minus 1 is an element of k in just k of S2. So k and it generates it.
Yes, but we need to quotient by h minus 1 squared is 0.
Yes, and so this is so suppose yes, maybe I forgot something to say. So we can after this we can get that there is no wait. So what I want to say, if we consider a product by h minus 1, we have an external product with h minus 1, we get an isomorphism of k tilde of x and k tilde of double suspension.
H minus 1 or h?
H minus 1. So why? Because this is just this is isomorphic to z with the generator being h minus 1, and this gives as it is z, it is just an isomorphism. So we get so the isomorphism is
how do you use this from the fundamental product theorem?
X goes to h minus 1. We will denote the external product like this, h minus 1 times x. How do we deduce it from here? Because this is an isomorphism. So we know that this is k of s2. So actually, not only composition is an isomorphism, but also both arrows are isomorphisms. And we know that yes. Yes. I forgot to say about tildes.
Yes, this is possible too. I suggest to have a break, 20 minutes, and then we continue.
Okay. So the thing is, we actually 1 minute till the end of the proof.